And this is a very, very non-trivial process. I won't be able to teach you how to do it with the time, but I want to give you a little impression of the difficulties and of the techniques we use as attackers to actually carry out this operation. Oren, you wanted to ask something? Hamming weight 3 does not mean by 3, right? Hamming weight 3 could mean, in fact, it doesn't. So it could be 7. It could be other numbers which have a Hamming weight of 3. How much is 3 plus 8? 11. Could be 11. Could be 16 times 3. 19. Okay, you got it. Fine. Hamming weight 3 means that there are only 9 possible values. So we have 9 classes, sir. We have 9 classes. Hamming weight 0, 1, 2, 3, all the way to 9. Okay, so I'm going to talk about the difficulties and give you some kind of insights about how do you do step 2 and step 3. So step 1, capturing a single power trace. That's, I talked about it 2 weeks ago. You connect and measure and find. Then you do some signal processing that's reasonable to do if you know something about it. We saw the Carl Leuven lab where they had the filter, so you can filter for it. So let's talk about this step, getting the Hamming weight of the state byte from the trace. And the game we have is, this is our input, and we have an output. The output is an array of 40 times 16. Okay, so the two challenges here that you have to deal with is that the first question we have to talk about is where, so this trace could be millions of points. Where is this happening? Where is this, this microsecond where the XOR is happening, where the add round key is happening, where the shift rows is happening, and so on. So we need to find the right place in the trace, which is equivalent to the right times at the beginning of encryption, and we need to say, okay, this is where it happens. This is where the key state, the state byte is being processed. And then what we need to do is we need to decode it somehow. So we need to take these maybe 100 or 500 or 20 points, interesting points. That's how we professionals call them. We need to take these interesting points and we need to decode. We need to output from these interesting points what is the Hamming weight being processed. So these two challenges, finding the right place in the trace to look at and getting the Hamming weight out of these points. Two challenges. So to answer the first challenges of where do we look in the trace, I'm going to have to travel in time to next week where I talk about correlation power analysis, because correlation power analysis is an awesome way of finding this. And I'm just going to be very, very brief. You're going to, and I think it's also, we'll also have to step on a little bit. You're going to look for places where if you change the this byte, the state byte a lot, you're going to get a lot of changes in the power consumption. So you're going to have, so the assumption is you're doing what's called a profiling step. You have to devise up the test, and you can put whatever you want into it. You're going to put in a known key, and you're going to play with it a little bit, and you're going to try to find a place where there's a nice correlation between, correlation, I said it, a nice correlation between the Hamming weight and this this power consumption. So I'm going to talk about it, God willing. So let's say we found the right place. Now what do we do with these these values? So now I've reduced my problem from having this huge 1 million point buffer and needing to output 100 Hamming weights, 100 times 16, 40 times 16 Hamming weights, to a more simple problem that I have, let's say, 50 interesting points, and I need to output 1 Hamming weight. So is this clear? So is this reduction clear? I'm going to deal now with, instead of getting all of the state Hamming weights from the entire trace, I did some hocus pocus trick, which I'll teach you next week, and now I found the exact interesting points in the trace, maybe 10 or 20 interesting points, and I know that these points represent the best way of, they represent processing the state byte, one of the state bytes I'm looking for, and now I need to write a decoder which takes these interesting points as input and outputs the Hamming weight. So is this clear? I need, instead of looking at the whole trace, I found the right place, and now I just need to look at these 5 or 6 or 10 points and output the Hamming weight. Okay, so I have some. Actually, I think I changed the polarity of the question in the middle, but I hope you'll survive. This is a tip of the tongue tour of this. So some very, very basic signal processing, and I think those of you who learn statistics might find something that they learned before that will teach you. So I'm going to be very, very briefly talking about something called template attacks, and this is the way of recovering Hamming weights from the trace. So again, I know where to look. I found out somehow where to look, and I just want to find out what is the Hamming weight of one state value. And the tool which is going to help me is the normal distribution. So the normal distribution is the Gaussian distribution, a very nice random variable, and very common in many situations. And I'm going to assume now that the interesting point, let's assume I have one interesting point, and this interesting point has it has a normal distribution around some kind of mean. This mean, here is the mean, the mu. And this mu is the right, it's the right voltage value for this Hamming weight. So I am going to do profiling. So I have a million traces I can use profiling with, and I take these traces. I find all the traces with Hamming weight 3, and I run them through. I take an average of them, and I find that at this interesting point, this is the average voltage for Hamming weight 3. Okay, I can do this with Hamming weight 1. I get this waveform, and I find this is the mean voltage for Hamming weight 1. This is the mean voltage for Hamming weight 2, 3, 4, 5, 6, until I get to 8. And now I have 8 mu's, 8 averages, 9 averages. So low complexity means online complexity. You're doing some processing in the beginning. This is like the kashe beimunim, hardened training step. You're doing this in your home before you get the device. This is like, and this is a known key. This is a very, very friendly and relaxed situation you're dealing with here. No, this is before you get to one trace. This is you're preparing. You didn't see the trace yet. You're trying to build a decoder. You're trying to build a machine that, given the trace, will output the Hamming weight of one of the state bytes. So I'm going to take training vectors that I found. I arranged them because I have the device in my control. I measured a lot of calculations with a Hamming weight equal to 1. And I found out that the waveform looks a certain way. And I found out this interesting point somewhere on the trace. Every time I process a Hamming weight of 1, we'll see this more clearly if we look at this again. Okay, this could be an interesting point. This sounds like a pretty interesting point, this one here. Okay, this interesting point, I see that every time that I process Hamming weight 0, this is the average power consumption I get. Every time I process 1, this is the average, and so on until I get to Hamming weight 8. So now I have 9 means, the mean for 0 all the way to the mean for 8, and also I can calculate, why is this long? Because I did it. And I can also calculate the variance, which means, I might have some noise in my system, so I'm not exactly measuring the exact Hamming weight every time. Sometimes it's less, sometimes it's more, but I can get this, so I can capture this I can learn Gaussian distribution. There are ways of doing it. Pretty standard ways. I'm not going to teach you. So now I have a vector. I have 9 possible Hamming weights. For each one of these Hamming weights, I have the mean and I have the standard deviation for this mean. And now the time comes where I'm actually given the trace. Okay, so I don't have time to talk about multivariate here. I'm apologizing, but I want to cover more text. Multivariate normal distribution means that you have, instead of 1 interesting point, you have 2 interesting points or 3. So it's basically the same thing, only the mean is a vector and the variance is a matrix. So I don't have time to cover this, so I won't. You're asking if the mean is for the entire trace. No, Sagi, I'm talking at a very particular moment in time. This is called the interesting point. One output of my oscilloscope, one instantaneous power consumption measurement, which is equivalent in this here, in this, I'm going to go back to slide 16, don't forget. So if I look at this, again, I need to look at one point in time. I'm going to look at this point in time. And in this point in time, you see that each one of the Hamming weights behaves differently. And then I can say, if the Hamming weight is 0, it's distributed this way. If it's 1, it's distributed that way. What does it mean distributed that way? It has this mean and this standard deviation. And again, there are tools of doing multivariate. I don't have time to cover it this year, I'm afraid. Just because we have so much awesome material, don't worry. So I'm not going to talk about multivariates. But now I need to work the other way around. So I learned my distributions. I know how Hamming weight 0 looks. I know how 1, I know how 2, I know how 3. I know how all the 9 classes behave. And now the moment comes, I got my measurement. So now I have 1 point. I have one point, one power consumption, one interesting point, and I'm trying to figure out which of the classes 0 to 9 did I measure. So I'll do it first of all the simple and incorrect way, and then I'll add you Bayes' theorem. So let's just assume for the sake of discussion that I found out that the Hamming weight 0 gives me a mean of 0 volts, Hamming weight 1 gives me 1 volt, and so on until Hamming weight 8 gives me 8 volts. Great. And now I'm telling you that I measured 1 volt. So what is the Hamming weight that I just measured? So the standard deviation is equal. All of them have the identical standard deviation. The standard deviation is 2. I measured 1, so Hamming weight 0 is 0 volts, Hamming weight 1 is 1 volt, Hamming weight 2 is 2 volts, and so on. And I told you that I measured 1 volt. So what is the Hamming weight that I just measured? Yeah, you're very, very careful, you know, that you think that I'm going to be tricking you, right? The answer does not mean that it's Hamming weight 1. And the problem, the reason is that because of Bayes' theorem. And again, I don't have time, I'm afraid, to cover this in detail. But when I'm trying to run this decoder in reverse, I don't only need to know what is the mean and standard deviation. I also need to know what is the probability of each one of these being output. And it's kind of shifted here. So this is Bayesian inversion. If one of the symbols is much more common than the other symbol, I'll prefer it, even if it's far away from the mean. And so what does it mean? It means that you know, if I put my hand out of the window in the summer in Israel, and there's a drop of water on my hand, I'm not going to say, "Wow, it's probably raining." Even though that's a pretty good indicator, if water is falling on my hand, that's a pretty good indicator that it's raining. But I know that it hardly rains in Israel, so I'm going to say, it's probably the air conditioner or something like that, or a bird or whatever. Because I know that the a priori probability, before I even make the measurement, the probability is very low. And again, because Hamming weights are not uniformly distributed, 3 and 4 are more common. I was doing this as a PhD student, it was driving me crazy. I wrote the decoder, and whatever I fed into it, it would say the Hamming weight is 3 or 4, even if the measurement was exactly the mean of Hamming weight 1. Why was it saying 3? Because the probability of 3 is so high. Okay, so if you want to learn more about this, you're going to have to read a very nice paper called Template the Text, and you'll learn the signal processing. But now we are in a happy situation. We have decoded all of the state byte Hamming weights. Wonderful. We have an array of size 100 by 16, right? 16 by 100, with all of the Hamming weights of the state. And now I want to recover the key. So how do I do it? I'm going to tell you how to do it because we don't have time. What you can't do is, I keep saying 100 and not 40. Oh, I'm saying 100. Yeah, that's a good question. The reason I'm saying 100 is that effectively an 8-bit microcontroller does 100 operations when it's encrypting AES, not 40. But you don't have to know that. Let's say 40. It's fine. Actually, it's doing 100 operations per round, 100 basic operations. But let's say I have 16 by 40. Doesn't matter. The same issue stands. I can't XOR this and that and get the key because I'm only processing the Hamming weights. And I only have one trace, so I can't do all sorts of sneaky stuff like reducing all sorts of. You have candidates, and I put in more and more plain text, and less things become possible. So what do I do? Effectively, I need to solve an equation set. My equation set, and this is something called algebraic side channel attacks. My equation set, yeah. Oh, this is a nice figure. I don't have to show you. My equation set is a set of equations in some kind of logic language. It says basically, this is what the device is doing. The device is taking the plain text, it's XORing the key. What is the key? I don't know. And then it's shifting and multiplying and adding and so on and so forth. And the bits of the state are evolving. And in the end, you get the ciphertext. But this is one part of the equation set. So the state is evolving in the function of the key. And the next thing in the equation set is saying, the Hamming weight of the first byte of the state, I don't know the state, but I know that the Hamming weight is 3. I know that the Hamming weight is 2. I know that this Hamming weight is 8. And I'm going to write this series of equations, and I'm going to deal this. I put this into an equation solver. The equation solver is a very nice piece of software which just looks for a solution to a series of equations. And there's a fantastic study of how to do them. Really not relevant to the course. To us, it's a very nice tool. You just need to find a tool which has a nice input format, because sometimes they're very hard to write for. So I write an equation set which says this is what the device does, and this is how the side channel is a function of the device, and this is what I measured, and this machine, runs for a while and outputs the key, which is awesome. It's really, really nice, really cool. But the problem is, what happens if I make an error in the code? So I need to give the equation solver my measurements, right? The Hamming weights of all of the measurements. But I have noise, I have errors. So if I have an error, I don't get the right Hamming weight fed into the solver. And then the solver has to go a little crazy. It's very hard to deal with. I'm telling you, I don't have time to show you how to deal with it. But I want to give you some kind of bonus content. I'm going to show you an actual equation set which I prepared ahead of time. How do I do this anymore? Can I open a new window on this? 1 second. 1 second. I'm going to share a window here with you. Awesome. And I need to share this. Yeah. So do you see this fantastic window? So what you see here is an equation set for AES. And I'm just going to survey what's going on here. This is the plain text assignment. So I'm saying the first byte is equal to 62, second byte is equal to 45, and so on. And this takes a long time. And the next thing that happens is key expansion. I need to expand the round keys. So I'm doing round key expansion. And the next thing that happens is encryption. So the first thing you do in encryption is add key. So I do XOR. So I XOR the first bit, the second bit, the third bit. I do XOR 128 bits. And you see it's very uniform. The next thing I do is subbytes, and here is subbytes. This is an equation set for subbytes. And again, this is very, very uniform. And the next thing I do is shift rows, mix columns. And the next thing I do is what's left? I forgot. I think that's, and then I say, this is the measurements. This is the Hamming weight for byte 1. This is Hamming weight for byte 2, and so on. So a lot of Hamming weight measurements. And yeah, it keeps on going. This is, and I put a hint for me, this is the correct key, just to make sure that the solver works. And this file, you feed it into a solver, and it might run for 3 hours on this input. And in the end, it will say, this is the correct key, the key that satisfies all of your equations. And again, if the equations are incorrect, this is a machine that this specific equation solver can deal with errors. But again, I don't have time to talk about it this year. So to summarize, very, 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 very quick run over simple power analysis. I need 3 steps to do simple power analysis for AES. First of all, I profile the device. I kind of understand, figure out what's going on. I build some kind of model. And then in an online phase, I get one trace. I figure out the Hamming weights. And then the next thing is I go from the Hamming weights to the correct key or several correct keys. And this can take many, many hours of post-processing time. Profiling, you know, on how many measurements we want. We have a device. We can run whatever code we want. This is the aim. This is Kasher Baimunim, difficult in training. We can profile as long as we want. Fine. So if you understood everything I told you, you are geniuses. It took me a long time to understand this as a student. But I hope what you understood here is that simple power analysis is not so simple, but